You know that feeling, right? You type maybe 2 letters into your phone and somehow it just finishes your sentence. It feels a little bit like magic, maybe even mind reading, but it's not. So today we're going to go full detective, crack open this autocomplete mystery and figure out exactly how machines learn to predict our very next word. Yep, we've all been here a million times. You start typing and boom, these suggestions just instantly pop up. It really does feel like a magic trick. But the secret, it's not magic at all. It's a technology called a language model, and it's all built on a really fascinating foundation of data and just probability.
All right, let's dive in. It's time to pull back the curtain and really investigate the secret behind this predictive power.
So the secret weapon here is this language model. Forget all that magic stuff. Just think of it as a super-powered probability calculator. Its entire job, its only purpose in life, is to look at a bunch of words in a row and figure out what is the most likely word to come next. But, to calculate probabilities about anything, you need evidence, a lot of evidence. For a language model, this evidence is called a text corpus. Just imagine a massive, gigantic digital library. We're talking all of Wikipedia, millions of books, countless news articles, everything. The model basically reads all of it to learn the patterns of how we, as humans, actually talk and write.
Okay, so the model has its library. It's read all the books. Now comes the real detective work, finding the predictive patterns that are hiding inside all of that text. Let's use this super simple sentence as our first piece of evidence. We're going to break it down piece by piece to see exactly how a language model would analyze it.
Now here's where things get interesting. The model doesn't read sentences like you and I do. Instead, it chops them up into these smaller, overlapping little chunks called n-grams. I know, it sounds a bit technical, but trust me, it's really simple. Let me show you what I mean.
So here's how it works for our little sentence. First, you have unigrams. That's easy. It's just each word by itself. Then you got bigrams, which are all the possible 2-word pairs, like the teacher, teacher drinks, and so on. And trigrams? Yep, you guessed it, 3-word sequences. The model then scans its entire library and counts literally billions of these n-grams to learn one very simple but incredibly powerful rule: which words are most likely to show up next to each other.
Okay, so we've got all our n-grams. The model has spent all this time counting them up. But so what? How do we actually turn a bunch of counts into a real prediction? How do we get from a simple pattern to an actual probability?
Well, it all comes down to some surprisingly simple math. To make this crystal clear, let's just pretend for a second that our model's entire library, its entire universe of knowledge, is just this one short sentence: I am happy because I am learning.
So here's the test for our tiny model. Based only on that one sentence, if the model sees the word I, what's the probability that the very next word is going to be am?
The logic is actually dead simple. You just take the number of times you see the pair I am, and you divide it by the total number of times you see the word I. In our tiny sentence, I am appears twice, and the word I also appears twice. So 2 divided by 2 is 1. That means our model is 100% certain that the next word is am. No doubt about it. Now this all seems pretty straightforward, maybe a little too easy, but our mystery is about to hit a major plot twist. What on earth happens when the model sees a sentence, or even just a long phrase, that it has never seen before in its entire library? And here is the fundamental problem. The longer a sentence is, the less likely it is that our model has seen that exact sequence of words before. And if the model has never seen it, what's its count for that sequence? It's 0. And if the count is 0, well, the probability is 0. The model basically just throws its hands up and says, impossible, and then it just shuts down. This means for any new creative sentence, our simple model is completely and utterly useless. So, to solve this massive problem, researchers came up with an absolutely genius shortcut. It's called the Markov assumption. It's just a simple rule that says, hey, to predict the next word, we don't need to look at the entire history of the sentence. We only really need to look at the last 1 or 2 words. And this right here is the big aha moment. Instead of doing it the hard way, trying to calculate the odds of T coming after the whole phrase, the teacher drinks, which is pretty rare, the model takes the smart shortcut. It just looks at the last word, drinks. Then it asks a much simpler question. What's the probability of T following drinks? That 2-word pair is way more common, so the model can make a much better guess. It's a clever trade-off of perfect precision for practical results.
So now that we have that clever shortcut in our back pocket, let's put all these pieces together and see how this one simple idea powers some of the most complex technology we use every single day. Seriously, this single idea, predicting the next word, is the engine behind so much of our modern world. Autocomplete is the obvious one, of course. But for spelling correction, the model just finds the most probable word that's similar to your typo. Even mind-blowing stuff like machine translation often works by just finding the most probable sequence of words in another language. It's all just probability, all the way down.
This brings up a really important question, though. If you have two different language models, how do you know which one is actually better? How can you tell which one is doing a better job at predicting text? We need some kind of scoreboard.
And that scoreboard is a metric called perplexity. The easiest way to think about it is as a confusion score. When a model reads a sentence, a high perplexity score means it was really surprised by the words it saw. It had no idea what was coming. A low score, on the other hand, means the text was pretty predictable and the model did a great job. So when it comes to perplexity, lower is always better. And this chart just proves it perfectly. Look at the bar on the left. A unigram model, the one with no context at all, has a massive perplexity score of 962. It's totally confused. But just add one word of context with a bigram model, and bam, the score plummets down to 170. With a trigram model, it's even better, at 109. The lesson here is crystal clear. The more context you give a model, the less surprised it gets, and the more accurate it becomes.
Okay, there is one last loose end to tie up in our mystery. What about those word pairs that have a count of exactly 0? To solve this, models use another little trick called smoothing. It basically borrows a tiny fraction of probability from the common word pairs and just sprinkles it over all the unseen ones. That way, the model's guess is never exactly 0, and it never gets completely stuck.
So when you boil it all down, everything we've looked at today is based on some pretty simple statistics, just counting which words tend to appear together. It's powerful, incredibly powerful, but it's not understanding. The model doesn't know what a teacher is or what tea tastes like, and that leaves us with a huge, fascinating question for the future, doesn't it? What happens when AI stops just predicting words and starts to actually understand the meaning behind them? Now that is the next chapter in this story.